Good morning, everyone. Thank you for coming. My name is Gong Hengte. I'm a master student from the College of Mechanical and Aerospace Engineering at Jilin University. It's a great honor to be here today. I'm presenting on behalf of my supervisor, Professor Chai Boson. Today, I will share our last date research. This topic is research on numerical simulation of flow fields and the vortex system reconstruction measured for hydraulic torque convergence. First, I would like to introduce the leader of this project, Professor Boson Chai. Professor Chai is the doctoral supervisor at Jilin University. He is distinguished expert in the field of fluid transmission and dynamic design. As you can see on the screen, his academic achievements are very impressive. He has led 18 major research projects, including projects for the National Natural Science Foundation of China. He has protected in 26 national level major projects. He has published 44 high-level academic papers and holds 14 penance. I want to highlight this picture at the bottom right. Our team developed a high efficiency hydraulic torque conversion for high machinery. This achievement was so significant that it was featured on CCTV famous show, The Pillars of a Great Power. This proves that our research is not just a theory. It solves real-world engineering problems. Now, a brief introduction about myself. I'm studying for my master's degree. My research focuses on two special areas: CFD simulation, using computers to solve complex field problems. PIV experience, using lasers and cameras to visualize flow. The image at the bottom shows the test rack I built and the flow particle recaptors. I will explain this in detail later. These improvements are the foundation of today's report. To make my proposition clearly, I have divided into 5 parts. The first is background of study. Why is this research important? The second is simulation methods. How did we calculate the flow? The third is PIV. How did we prove our calculation is correct? And vortex and size. Comparing different measures to find the vortex. The last is conclusion. What did we learn? Let's start with part 1, background of study. Please look at the machine in figure 1. This is a loader. It is a very common machine in construction. Inside the machine, this is a key component called the hydraulic torque conversion, or HTC. Why is the HTC is so important? It acts like the heart of the transmission system. It transfers power from the energy to the valves using liquid ails. If the HTC is efficient, the machine saves fuel. If the HTC is smooth, the driver feels comfortable. However, designing a good HTC is very difficult. Why? Because the flow inside is actually complex. Please look at the figure 7 and 9. The liquid inside moves at a very high speed. The internal pressure changes rapidly. We call this high Reynolds number turbulence. As the liquid flows through the curved blanks, it doesn't move in a straight line. It swells, it separates, and it creates vortex. What is the vortex? Think of this like a small tornado inside of the liquid. In figure 7, you can see these complex vortex structures. These vortex are energy keys. They consume energy, which low frequency. They create noise and vibration. They can even damage the plants. So our goal is simple but hard. We need to see this vortex clearly. Only when we see them can we fix them. So, how do we see the flow? First, we use computer simulation, or CFD. This is our simulation process. The most key choice here is the turbulence model. We did not use standard models. We chose the SBE model. Why SBES? Because it combines the best of two worlds. Near the wall, it uses a stable model, RANS, to handle the binary ladder. In the open flow, it uses a detailed model, LES, to solve the vortex. Also, we set a very small time step, 0.001 seconds. This allows us to catch very fast transition changes. Next, let's look at the mesh. A good simulation needs a good grid. We use the Hydraul mesh. These are brick shift shells, which are very accurate. We made the cells very small, near the plant safe surface, to capture the fraction. This chart shows our grid independence test. This is very, very important. The axis is the number of grid cells. The red line is the error rate. The blue bars are the concurration time. You can see that when we reached 5.6 million cells, the error rate dropped to a very, very low level. Adding more cells increased the time, but didn't improve accuracy much. So 5.6 million is our sweet point. How do we know the calculation is finished? We look at the residues. In figure 14, you can see these lines going down and staying flat. These are below 0.001. This means the mesh is stable. We also monitor the top torque of the turbo, pump, and state. Look at these curves. In the beginning, they go up and down, but after some time, they show a regular pre-torque pattern. This tells us the flow point has fully developed and is ready for analysis. Now, we have the simulation results, but can we trust the computer? This is a question. We must verify it with a real experiment. To validate the data, we built this PIV test drag, shown in figure 19. PIV stands for particular image volley symmetry. Here is how it works. We put tiny particle into the water. We sort the scene laser shift. That is the green light into the machine. A high-speed camera takes 2 photos very, very quickly. By comparing the 2 photos, we can calculate how fast the particles are moving. Notice the model in the center. We made it out of transparent. This was very difficult to manufacture, but is along the laser pass-through so we can see inside. Before measuring, we had to solve a big problem. Optical destruction. Because the model is curved and filled with liquid, the image looks burnt, like looking through a glass of water. To fix this, we performed external calibration. We marked the outer edge of the model in the mesh with the real physical size. For example, the number 1188.81 you see here is a calibration parameter. This ensures that every picture in our photo corresponds to the actual physical lines. We measure that to specific positions z equals 0 and Z equal 25. This is the most important field. This is the moment of truth. Left me image our CFD simulation result. Right image our PIV aspirate result. The color response speed. Red is high speed, blue is low speed. Let's compare them. Region A, this is the turbo inlet. The liquid is shooting in very, very fast. The simulation predict about 13. The experiment measured 31.2. The difference is very, very small. The shape of the red zone is almost identified to region B. This is inside the channel. The flow separate here, creating a snow zone. Both images show a clear blue bond. The speed is between 5 and 9 in both cases. Conclusion: because the colors, shape, and the number matched so well, we can say our SBS simulation is accurate. Next, since the simulation is accurate, we can now use it to variable the vortex. We compare the three measures, Q, omega, and our focus, the omega vortex. Let's look at the overall structure. Far left, this is Q. Look at the green shapes. They look broken like a disconnected sausage. It fails to show the full picture. The middle is omega measure. It's better, but the structure look very thin. Some connection are missing. Far right is omega vortex. This is our focus on. Look at this one. It shows a complex, connected, and dense network of vortex. It reverses the truth of the flow. Next, let's zoom into the pump. Please look at the entrance of the blend. Red image, omega vortex. You can clearly see a counter vortex. It looks like a long continuous curve. Left image is Q. It shows almost nothing here. If we use Q measured, we might think this is no problem. But vortex told us this is a vortex that need fixing. Now the scatter, the flow here is very, very minor because of the secondary flow. The omega vortex measured capture not just the big vortex, but also many thin weak vortex. It is very sensitive to details. Finally, the turbo act here. We have weak vortex, so once traveling behind the blind. This causes noise. The traditional measures, left and middle, that is Q and omega. Show the vortex broken and disappearing quickly. This is not physical real. The omega vortex measured shows the vortex and moving far downstream. This helps us understand where the noise comes from. To summarize the compare, I made this star rating chart. Let's look at the omega vortex merge in the last column. For overall reconstruction and structure details, it gets a perfect 5 stars. It's missed nothing. For pumps and turb details, it gets 5 stars. It is excellent. I defined almost everything. Now look at the Q and in the first column. It only gets 1 or 2 stars in difficult area because the vortex are broken. This chart clearly proves that omega vortex is the separate measured for this type of the flow. In conclusion, our research has led to 3 key findings. The first is simulation is accuracy. We prove that the SBS model is highly accurate. It matched the PIV experiment in both flow, structure, and velocity wells. The second is overall performance. We find that the omega vortex measured is most repellent. It's not sensitive to sensor setting and can reconstruct the most complete vortex network. The second is the finally detail capture. We find that omega vortex is the separate at capture weak and dynamic vortex, such as counter vortex and weak vortex. That is all my conclusion. Today, I'm very happy to that concludes my presentation. I'm Gong Hengte. I would like to thank Professor Chai for his guidance, and thank you all for your time and attention. I'm now happy to answer every question you may have. Thank you very much.